What is the constitutive relation when it comes to structural mechanics? Okay, when we are not talking about thermodynamics and all. So the constitutive relation is this relation right here, the relation between stress and strain. And we are familiar with one of the constitutive relations that goes something like this: uh, sigma equals d epsilon. Okay, so there are two ways to look at this. If you represent them in so-called Voigt notation, where you can represent the stress, and for Voigt notation I use a bar, okay, as a vector. For example, sigma xx, sigma yy, sigma zz, then sigma xy, sigma yz, sigma zx. Okay. And similarly, the strain is represented like this: epsilon xx, epsilon yy, epsilon zz. Okay, but when it comes to shear component, it is gamma xy, gamma yz, gamma zx. Okay, I've said this, I believe, more than once, but I'll still repeat. So these quantities are essentially twice epsilon xx. So for shear components, when we go from matrix representation to vector representation, we go with the multiplication of two. Okay, and there are certain reasons for doing that. Uh, So of course the shear components are, symmetric and have the same value for x, y, and yx. Okay, but this coefficient of two serves this purpose, that when we, let's say, if I want to do the inner product of uh, stress and strain. Now this time they are represented as matrices. So this quantity would be summation over I, summation over j, sigma ij, epsilon ij. So basically you take each component of the total 9 terms, 3 times 3, 9 terms of sigma, and take the corresponding component of the strain, multiply the two, and keep adding those products. Okay, so that is this term means. So this is like the inner product of the two matrices. Now that inner product can simply be represented with this dot product right here, which the dot product is again an inner product, but with involving two vectors. Okay. Now, if I had not multiplied 2 over here, in this case, I'll be having total 6 terms. So sigma xy times epsilon xy and so on. But if I want to add sigma yx times epsilon yx, that is essentially same as sigma xy times epsilon xy, because you see the matrices are symmetric. So how can I achieve that? By simply putting a coefficient of 2. So when it comes to the strain components, the shear strain components, a coefficient of 2 is put in the so-called engineering notation. Now this is different from engineering strain. Okay, so that engineering and true strain, that is different. Okay, here it is engineering notation or Voigt notation. um One more thing you might notice, that I'm taking inner product of two matrices and inner product of two vectors. Okay, sigma and sigma bar is different. So sigma would be this quantity. Sigma would be like sigma xx, sigma yy, sigma zz. Okay, sigma xy, sigma xz, sigma yz. Okay, and so on. Okay, it's a symmetric matrix. So uh, so this multiplying the strain matrix, okay, as I explained, using term by time multiplication, and the same thing can be achieved by taking dot product of these two vectors. Okay, now when I'm representing the stress and strain in Voigt notation, then the matrix that so this is a 6 cross 1 matrix, and this is also a 6 cross 1 matrix. So the matrix that you know represents a correlation. So these are all in linear elasticity. Okay, so that is a 6 by 6 second order tensor. But if it is like 3 by 3 matrix form instead of the void form, so in that case it's a 3 by 3 by 3 by 3 fourth order tensor. Or in other words, sigma ij is summation over k, summation over l, going from 1 to 3 each, dijkl times epsilon kl. Okay. So this is the so-called constitutive relation, essentially the relation between the stress and the strain. Okay, and now today we'll look for the constitutive relation in plasticity. Okay, এই পার্টটা বোঝা গেল কি বললাম?
Yes, sir.
Okay. Now to look into the constitutive relation of plasticity, first we'll start with this equation. I'm a bit confused. Should I take uniaxial counterpart or let's take uniaxial counterpart. So okay, so let's take the tensorial representation. So I'm taking the stress and taking inner product with plastic strain, differential plastic strain. Okay, these are all matrices of size 3 by 3, and I am taking, so this basically means summation over I, summation over j, sigma ij, and the plastic strain differential, the ijth component of that. Okay, I'm simply doing that. Okay, so this could also be represented like the equivalent stress and equivalent plastic strain increment. Okay, so this can also be represented like this, and essentially this represents plastic dissipation, the differential plastic dissipation, and that quantity is greater than zero. Okay, we'll start with this inequality. Okay, now of course this inequality has a background from thermodynamics. Okay, and that's quite extensive. Okay, so there is couple of pages of thermodynamics behind this equation or this inequality, and for the time being at least, we would not go into that. But is it difficult to appreciate that if there is a plastic deformation, there would be dissipation? Okay, that's what it really means. Is it really difficult to appreciate? এটা কি মানতে অসুবিধা আছে?
No, sir.
Okay, so basically, if there is plastic def- def- uh, deformation, there would be some energy loss. That's what this means. Okay, now let's say this is the uniaxial stress strain diagram in plasticity. Okay, and let's say this is a stress sigma star smaller than the so-called yield stress. Okay, and I would mark one point A over here. Okay, and then I'm drawing a line parallel to the elastic part of it, which intersects with the stress strain diagram at B. Then I will take a differential strain, or let's say differential plastic strain. So I'm showing the differential strain, but in calculation I'll only be taking the differential plastic strain, which makes me arrive, or sorry, this is the differential plastic strain. Okay, so because yeah, so this is a differential plastic strain. So because once I unload, there is a part that cannot be that cannot be recovered. If I unload, this part can be recovered, but that part cannot be. Okay, so and this other intersection point is D. So these are 4 points. Okay, going from A to D, A B C D. Okay, now we know that uh, let's say if I were to start from the origin and were to deform along the loading curve. So this is a loading curve, let's say. Now at any point, if I unload, let's say at B, if I unload, okay, so we know that the B becomes new yield stress. Okay, so if you unload from here, okay, uh, so B is the new yield stress. So you might notice that this is not a elastic perfectly plastic curve. Instead, it's elastoplasticity with hardening. As in, as the strain progresses, the stress also increases. Okay, now if I were to unload from B, okay, I would be unloading that along a line that is parallel to the elastic part. So I'll be following this curve, and let's say if I unload to up to sigma star, then I reach this point over here. uh, uh, then that so I reach this point A. Okay, now, if I reload from A, okay, I'll be reaching B first, then I'll be moving from B to C, and then if I unload again, then I'll be reaching D over here. Okay. Now, now, uh, by the way, this part is greater than or equal to zero. Now, when is it equal to zero? When the plastic work done is equal to zero, when the stress is actually below uh, the yield stress, and by that that means when the material is deforming elastically. Okay, so if this is the unloading curve and also the reloading curve, this curve is actually your elastic curve, which basically means when you go from A to B, the deformation is only elastic. Okay, so when you go from A to B, okay, that deformation is elastic. So by that, we mean is that your the the plastic work done is actually zero. Okay, but then again, when you go from B to C, there is some plastic work done, and then from C to D again it is zero. So the net work done is going from A to D integration sigma uh, minus sigma star d epsilon. Okay, so we are only considering the additional work done, okay, for unloading up to sigma star and then going above this. Okay, so we are only looking into this area right here. Okay, so so this quantity is actually greater than 0. Okay, now how much is this area? This area is comprising of this portion times d epsilon, which is this parallelogram. Okay, that is sigma minus sigma star times d epsilon. Okay, so this is the area of this parallelogram. Then the additional part is, you see, if this portion is d epsilon, so this is d sigma. Okay, now you can very well regard to this as d epsilon p. So in addition to that, you have this triangular area whose area would be d sigma, half of d sigma times d epsilon. Okay, and that is greater than 0. Okay, now you can think of two conditions. One is, you know, now what stress is sigma? Sigma is the stress at B. So the point at which you started unloading, that is the stress sigma. Okay, and that becomes your new yield stress. Okay, so if we were to have further plastic deformation, so up to B there is only elastic deformation. From B starts your plastic deformation when you reload the material. So uh, so there are two conditions. One is if sigma uh, minus sigma star is much greater than d sigma. In that case, actually you can neglect the second term, and then you can say that sigma minus sigma star times d epsilon p is greater than 0. And this is true for all sigma star. Okay, and now what do I mean by sigma star? You see, sigma is the stress of the point from which you started unloading, and sigma star is that arbitrary stress below the current yield stress, okay, where you are unloading. Okay, so sigma star is pretty much arbitrary. Okay, and therefore this relation must be true for any arbitrary sigma star. Okay, now on the other hand, if sigma were equal to sigma star, in that case you can neglect the first term and you can claim that d sigma d epsilon is greater than 0. You see, sigma star is arbitrary, so I can take it much different from sigma, or I can take it to be exactly equal to sigma. Okay, so I can take sigma star to be exactly equal to sigma. So both of these results are true always. So this result and this result are both true all the time. Okay, because this proof right here is for an arbitrary sigma star. Okay, below the uh, below the yield stress. So now we'll interpret. আচ্ছা এই অবধি কি বোঝা গেল?
হ্যাঁ স্যার।
দুজনেই বুঝতে পেরেছো? Okay. Now let's look at this expression. You can interpret this to be sigma minus sigma star. This time I'm not taking the equivalent values. So this was an exercise involving equivalent quantities. Okay, so these were kind of uniaxial. In multi-axiality, you can interpret that to be the inner product of this with d epsilon p is always greater than 0. Okay. Now, this expression right here okay, can be further interpreted like this. Okay, so let's say these are your principal directions. Okay, and imagine this is your yield surface. Okay, be it von Mises or Tresca criteria, whatever the case may be. Let's say that is your yield surface. Okay, and I'm just showing that on a given plane. Let's say the divisory plane. Okay, and you are talking about a stress sigma star which is well within the domains of elasticity. Basically it is inside of the yield surface, and there you have okay your stress, current stress, or let's say the point B from which you started unloading and reloading. Okay, now at this point, although this is stress space, but if I were to show the direction of the strain rate, okay, you see this is stress space, this is not strain space. But even so, let's say for the sake of only direction, if I were to show the differential strain vector, okay, you see this is your sigma star vector, this is your the current stress vector in principal directions. Okay, but if you see this, the plastic strain increment right here, the claim is that okay, I shouldn't be taking sigma star over here, it's a little confusing. Let's say if I take sigma star over here, okay, so this is the vector sigma minus sigma star. Okay, and this inner product, again, when you represent this thing in principal coordinates, it is in principal coordinates, again you can represent sigma to be like sigma 1, sigma 2, and sigma 3, and epsilon d epsilon p to be like d epsilon p 1, 2, and 3. Okay, so like three-dimensional vectors. So again that becomes a dot product. Okay, and here we are talking about this sigma minus sigma star in the principal coordinates taking dot product with d epsilon p is always greater than 0. That is, it is always non-negative. But what does that mean? Non-negative means that the angle between the two, this angle right here, it is always less than 90 degree. Okay? It is always less than 90 degree. It is not greater than 90 degree. If it were greater than 90 degree, the dot product would be negative, right? Can you follow this?
Yes, sir.
Okay. So obviously this angle is theta is an acute angle. Now this representation is only valid when the stresses and strains can be represented as three-dimensional vectors. So we learned to represent stress and strains as 3 by 3 matrices, six-dimensional vectors, and then in principal coordinates they are three-dimensional vectors. So when they are principal in the principal coordinates, they can be represented as three-dimensional vectors, and then this product right here, this inner product right here, okay, or this product right here, essentially becomes a dot product, and then we can really talk about this angle theta, which needs to be an acute angle. Now this is only possible if the following are true. Number one, yield surface, be it von Mises criteria or Troska criteria or whatever criteria, is convex. It has to be convex. I mean, the yield surface cannot be like this. Then let's say this point is on the yield surface, sigma. Okay, then you have, it's a some plastic strain. Sorry, there's plastic strain increment right here. And let's say this one is your sigma star. Then you can imagine that if I were to draw sigma minus sigma star, that vector makes an angle of theta which is greater than 90 degree. Okay, and then therefore it would not be possible for us to satisfy this condition. Okay, এটা কি বোঝা গেল কি বললাম? যদি yield surface টা convex না হয় concave হতো, okay, then there you would find the stresses within the elastic limit, a sigma star which is within which is inside the yield surface, okay, but sigma minus sigma star, okay, uh, is at a higher angle than 90 degree with the plastic strain increment, okay, and this condition would be void because the dot product would be negative. এই পার্টটা কি বোঝা যাচ্ছে?
হ্যাঁ স্যার।
Okay, and then there is condition number 2, and that is actually simple. Since this is true for any stress sigma star, sorry, any trial stress sigma star uh, less than or equal to sigma, that is the uniaxial case. For multiaxial case, sigma star can be anywhere inside the yield surface or by extension anywhere on the yield surface as well. Since it can be anywhere inside the yield surface, you can imagine it is just at the boundary. Okay, and let's say very close to sigma. Okay, the point is if you draw a tangent, okay, at sigma, so it can be so let's call that tangent as et. So that means sigma minus sorry, and if it is on the yield surface, if sigma star is on the yield surface and very close to sigma, so I can imagine, let's say it is sigma plus or minus h times limit h tends to 0, okay, times et, the tangent vector at sigma, okay. So therefore sigma minus sigma star is minus plus h times et, of course limit h tends to 0, And therefore, if I imagine, therefore I'll have to, if I take dot product with d epsilon p dot d epsilon p, that would essentially be minus or plus h et dot d epsilon p. Okay, and that needs to be greater than or equal to 0. I mean, if it is both plus or minus, if it has to satisfy both for plus h and minus h, the only way it can satisfy is that this product right here is 0. Then this condition is satisfied for both plus h and minus h. That means if sigma star is at the boundary and at very close to sigma, and it can be on the either side, and still this condition has to be satisfied, the only way that is possible is if d epsilon p is normal to the tangent, or by that I mean that it is normal to the yield surface. এই পার্টটা কি বোঝা গেল কি বললাম?
হ্যাঁ স্যার, কিন্তু এইচটা
এইচটা এইচটা হচ্ছে একটা স্কেলার, আর স্কেলার মানে একটা জাস্ট একটা নাম্বার, ধরো 10⁻⁵ or 10⁻⁻15. Okay, so it tends to 0. So if sigma star can be any stress within the yield surface. Okay, এখন এই within কথাটা is for a continuous system, because sigma star can have any real value, okay, less than the yield, what satisfies the yield condition. So you can also imagine that it is lying on the yield surface. Okay, there are cases where it is also lying on the yield surface. Number one. Number two is that if it is very close to sigma, okay, then you can imagine this tangent, okay, is essentially representing this arc right here. If it is very close to sigma, the tangent at sigma is essentially a portion of this arc, very close. Okay, so আমি যদি কার্ভটাকে জুম করি, okay, and let's see if this is sigma, and let's say this is where I'm drawing the tangent. Okay, for very tiny value, okay, plus or minus h, I can imagine these 2 points lie on the surface, and for them also this condition needs to be satisfied, and that is this condition right here needs to be satisfied, and the only way that satisfies is, and that too for both plus and minus h, is when actually the equality holds. That means equality holds if sigma star is on the yield surface. Okay, that this dot product of sigma minus sigma star dot d epsilon is equal to 0. That is only true um, when you are on the yield surface. How to interpret that? There is one situation where sigma star is sigma, so this whole quantity is 0. But if even if sigma star is not sigma, okay, but it is close to sigma, then also we can show that the only way that would be possible is when d epsilon p is normal to the surface. Okay, so the point is the plastic strain increment for a given stress is normal to the yield surface. Okay, now this equation or this inequality can also be written as which basically is the maximum plastic dissipation theory, which says of all possible stresses. You see, sigma star can be uh, any stress, right, within the yield surface and as well as on the yield surface. Now, if it is on the yield surface, the plastic deformation is possible, right? Now, this inequality means of all the possible values of stress, okay, the stress only assumes that value, or you need to remember by value I mean all the 9 components of it, because stress is a matrix, or on principal directions it's a vector. So all the components of it, so it assumes only that value that gives the maximum dissipation. You see this inner product right here, okay, is more than inner product. So for a given strain rate, okay, or for a given plastic strain increment, okay, uh, you arrive at a given stress value so that you have the maximum dissipation of all the possible stresses that you can have. Okay, there's just reverse of this statement right here. Here we are talking about the plastic strain being normal to the yield surface, so we are characterizing the plastic strain. Okay, whereas here we are talking about the possible stresses. Of all the possible values, the stress assumes only that value that would for a given plastic strain increment. Or here we are talking about a given stress. For a given stress, the plastic strain is normal. Plastic strain increment is normal to the surface, yield surface. Okay, and here we are giving a given plastic strain increment. Okay, if we are given a plastic strain increment, then we can say the stress assumes the value that gives the maximum dissipation. Okay, I mean on the yield surface also you could have had any other sigma star, right? Any other stress you could have had, but the stress only assumes that value on the yield surface that gives you the maximum dissipation. Okay, so these two statements, okay, just the two sides of a coin. Okay, বুঝতে পারছো তো দুটো স্টেটমেন্ট কি? একটা স্টেটমেন্ট হচ্ছে যে তোমাকে যদি স্ট্রেসটা বলে দেওয়া থাকে যে ইল সারফেসের উপর আমার এত স্ট্রেস হচ্ছে, then you can identify the direction of the plastic strain increment, which is essentially normal to the yield surface. Okay, number one. And the other statement is if you are given a plastic strain increment, okay, then you can identify what sort of stress would it assume on the yield surface. Okay, so it will assume that particular value of you know um, that particular value on the yield surface that actually makes the plastic dissipation maximum. Okay, now in principal coordinates at least you can identify the stresses and the strains as vectors. Okay, now let's say this is the center of the yield surface, or for that matter the axis of the yield surface. Okay, and okay, so we'll look into this later, but I hope you understand the two statements. Okay, এই পার্টটা ক্লিয়ার তো?
হ্যাঁ স্যার।
Now this is the equation of the yield stress. Okay, so for example for von Mises, And what is J2? Okay, I'm just giving you an example. And for the maximum shear stress theory, so this is for the distortion energy theory. So maximum shear stress theory, assuming sigma 1 is greater than sigma 2 is greater than sigma 3. So sorry. So the maximum shear stress is sigma 1 minus sigma 3 by 2. Okay. And sigma y is twice tau y. So sigma equivalent is actually sigma 1 minus sigma 3. So you see, by 2 is the maximum shear stress. And this maximum shear stress, so this is the tau max. And this tau max must go to tau y for yielding. Okay. Now sigma y is twice tau y. Okay. So basically the sigma equivalent would be twice tau max. Okay. So the point is that that we are talking about, you see, your plastic strain increment to be normal to the yield surface. Okay. Now, what is the direction of a normal to a surface whose equation is this? Do you know how to get the normal to a given surface? For example, if if the equation of a surface is phi equals 0, okay, phi is, let's say, certain functions of x, y, and z, okay, and that is the equation of the surface. How do you get the normal to a given x, y, z?
স্যার প্রথমে ট্যানজেন্টের ইকুয়েশনটা বের করবো, স্যার ট্যানজেন্টের নতিটাকে নর্মাল করে দেবো, -1 করে দেবো কোনো একটা
এই
পয়েন্টে।
জিনিসটা আমার ধারণা তোমাদের এটা আন্ডারগ্রেডে পড়ানো হয়েছে, বাট তোমরা হয়তো ভুলে গেছো। That if I take a gradient of the scalar, that gradient actually becomes the normal. By gradient, I mean taking derivative of f with respect to the stress components. Okay. And that actually is the direction to the normal to the surface at f, surface f at a given stress value. Okay. এই জিনিসটা কি খেয়াল আছে যে গ্রেডিয়েন্ট নিলে সেটা নর্মাল হয়?
না না স্যার, মনে পড়লো।
মনে পড়লো? আচ্ছা, আমি একটা জিনিস মনে করিয়ে দিই আরো। ধরো একটা সারফেস রয়েছে এফ, ওকে, বা ফাই, ধরো একটা সারফেস রয়েছে, এইটা হচ্ছে তার গ্রেডিয়েন্টের ডিরেকশনটা, ঠিক আছে? এবার এবার ধরা যাক এটা হচ্ছে ফাই প্লাস ডি ফাই, ঠিক আছে তো? মানে it's a parallel surface, you can imagine. It's not exactly parallel, but if you change the x, y, and z, okay, you get this value. Okay. So if you independently change x, y, and z, so let's say you get this value. And that d phi, you can imagine, is a gradient of phi. So basically this quantity is del phi del x dx plus del phi del y dy plus del phi del z dz. Or in other words, it's a dot product of gradient of phi, which is del phi del x del phi del y del phi del z, with dx vector. Now this dx vector is essentially this quantity, dx, dy, and dz. Okay, so let's say this is your dx, dy, dz. Okay, and as you can see, keeping the magnitude of dx, dy, dz same, okay, you get the maximum value of change of d phi, okay, when your dx is aligned with gradient of phi. You get the maximum value when these two are aligned, right? That is when you get the maximum uh, dot product. dx, dy, dz এর ম্যাগনিটিউডটা চেঞ্জ না করে, if I align dx along d grad of phi, that's when I get the maximum derivative. That's what it means by dot product, right? Now, একটা জিনিস দেখো, on this whole surface, this phi has a single value. Okay, let's call that value equals phi. Let's say I'm talking about phi equals x plus y plus z square or something. Okay, এবার ধরো যাক x equals 0, y equals 0, and z equal 1. So this phi has a value of 1. Okay, but if I take different set of x, y, and z, the phi value would be different, phi plus d phi. Okay, now now phi value would also be equal to 1 if x equals half, y equals half, and z equals 0. Okay, or x equal half, y equals 0, and z equals 1 by root 2. There are so many combinations in which phi can be equal to 1, and all of those are represented by different coordinates on a given phi. So everywhere on this surface, phi has a value of 1. Okay, and and if you move tangentially, so you are at this coordinate x, y, and z represented by this x vector. So at this coordinate, okay, if you move tangentially to the surface, you have the least variation of phi. Basically, the phi variation would be 0. Okay, because you would still be on this surface, right? If you move tangentially, that means you are being on the surface. So basically, the variation in phi is 0. Okay, so that means grad of phi dot dx would be 0 if dx were tangential. Okay, and also the maximum variation. Achha, now by this, what do you get? If I move tangentially, there is no variation in phi. So d phi equals 0 if dx is proportional to et. Okay, which means grad of phi dot et is 0. এ থেকে কি বোঝা যায় যে gradient is normal, and as you, if dx were to be parallel to grad of phi, you'll have the maximum variation of phi. Okay, তো এখান থেকে আমরা বুঝতে পারলাম যে gradient of a given scalar would represent the normal to the surface. Okay, represented by the value of that scalar. এই পার্টটা বোঝা গেল তো?
হ্যাঁ স্যার।
Yes, yes.
Okay, so so d epsilon p now can be, you see I'm representing that as a vector or a matrix, is, let's say, the scalar d lambda, because I don't know what is the constant of proportionality, times del f del sigma. Which basically is the gradient of f with respect to sigma. And that expression right here okay, is going to be the most important equation for us, or rather this is the constitutive relation that you are looking for in plasticity. Okay, so this is going to be the most important equation for possibly the rest of the classes. Now let's say if I take derivative of Tresca criteria in principal directions. So AF, as you know, is sigma equivalent minus sigma y. Okay. Now how much is del F del sigma in principal coordinates? So you see sigma y is a material property. So you don't get to take derivative of that. Okay. But if I take derivative of this quantity right here, del sigma equivalent del sigma 1, what would be the value? If I take del sigma equivalent del sigma 1, what would be the value?
স্যার বুঝলাম না, একবার বলুন।
I'm trying to get the gradient of f, right? So for Tresca criteria, f is for any criteria, af is sigma equivalent minus sigma y. Now this is either a material property or a function of plastic strain. So this is not a function of stress. So when you do take derivative of f with respect to partial derivative of f with respect to sigma, you essentially take the derivative of sigma equivalent. Okay. Now, what is the derivative of sigma equivalent when represented in Tresca criteria? This is the expression for sigma equivalent. Sigma 1 minus sigma 3. So, yeah, of course, you can take derivative in principal coordinate system or any arbitrary Cartesian coordinate system. But for Tresca criteria, let's choose the principal coordinate system. So in principal coordinate system, if I were to take the gradient of sigma equivalent, or for that matter, gradient of f, what would be the value? এই যে এক্সপ্রেশনটা, এটাকে আমি যদি সিগমা 1 এর রেসপেক্টে ডেরিভেটিভ নিই, কত কি হবে? পার্শিয়াল ডেরিভেটিভ
1
সিগমা 2 এর রেসপেক্টে নিলে
0
0
সিগমা 3 এর রেসপেক্টে নিলে
-1
-1
okay, so this gives you the direction তাহলে একটা জিনিস দেখো, if this is sigma 1, this is sigma 2, this is sigma 3. This is Tresca criteria. Okay. For some reason এটা ঘুরে গেল, but this vertex should be on this line, okay, as seen from the deviatory plane or the octahedral plane. So look at this line. Right? Okay. So when we are talking about, let's say, when sigma 1 is greater than sigma 3, and I don't know. So maybe we can take this line right here. So d epsilon p is normal to that side of the hexagon. Of course, it's not a hexagon. It's actually a hexagonal prism, the yield surface. Okay, and we are looking at its projection as seen along the hydrostatic axis. So we are looking at its projection on the deviatoric plane. Okay, so we discussed about this in one of our previous classes a lot. So if that so in that plane, it would simply look like it is normal to this side over here, and then over here it is also the outward normal. So on each side it is the outward normal. Now when you come to one of the vertices, okay, uh, then actually at the vertex, so these are the directions of plastic strain when you are at the corresponding stress value. But if you are at the vertex, okay, you know, both the sides, the normal to both the sides are possible normal, or actually any normal in between these two normals, okay, is the direction normal to the yield surface. Okay, so at a vertex there are infinite number of normals possible between the two normals. So let's call it normal 1, okay, a1, and this one is a2. So the actual normal a is an arbitrary combination of a1 and a2, okay, where a squared plus b squared equals 1. So an arbitrary number, infinite number of possible normals are there. Okay, but you might choose to take an average of these two normals. So you can take both alpha and beta to be 1 by root 2. Okay, so you can take it like that. um, so that is one issue that we have with a non-smooth yield surface. Okay, and such issue would not be there, as you can imagine, with Tresca criteria, because that sorry with von Mises criteria, because you have a smooth surface. Okay, now when you take আচ্ছা, এই কথাটা বলার আগে this expression right here is Levy Mises relation. Okay, uh, but you don't. I didn't simply give you that relation. Okay, that d epsilon p is d lambda times del f del sigma. You'll have to get there. Okay, and we got there by showing that the plastic strain increment is normal to the yield surface. Okay, so this is an important result. Okay, you can go through your textbook regarding Levy-Mises representation. Okay. Now you would look at the von Mises criteria and sigma equivalent as we represented. And this time we are using full 3D coordinate system. We are not using uh, we are not using the principal coordinates. Of course, we can use principal coordinates, but we will be using the uh, your general Cartesian coordinates. So, so of course, AF is as we represented sigma equivalent minus sigma y, and therefore del f del sigma is essentially del of sigma equivalent del sigma, and so I'm taking a gradient. So now I can I can write first of all this to get this expression. I can write it like this: 3 by 2 s inner product s. Okay. So therefore, I can write it to be twice sigma equivalent del sigma equivalent del sigma is del sigma of this quantity. Okay. So that implies del sigma equivalent del sigma is 1 by 2 sigma equivalent times del sigma of this quantity S inner product S. So S, you might recall, sigma minus sigma m times I, or sigma m is a trace of sigma divided by 3. Now S inner product S is actually sigma minus sigma m times I inner product S. Okay, I'm just replacing one of the S's with this expression. Now I am just not showing all the steps. Okay, this point onwards, so far I have shown. Okay, but this can be written as, you see, inner product is a linear operation, so you can you know use the distributive rule in it. Now, what is the inner product of the identity matrix and the divitoric stress? What is the inner product of any matrix with identity matrix?
স্যার ও
সেল
ডায়াগোনাল
ম্যাট্রিক্স থেকে।
ম্যাট্রিক্সের ইয়ে হবে।
Uh-huh.
তো ইনার
Same
প্রোডাক্টটা
matrix কি
ডায়াগোনাল
হবে?
ম্যাট্রিক্সটাই যাবে, মানে ডায়াগোনাল ম্যাট্রিক্সের
না
মানগুলো
না না
আসবে।
না, ডায়াগোনাল ম্যাট্রিক্স না, ডায়াগোনাল ম্যাট্রিক্স না, শোনো কথা। You are taking inner product. Inner product is a scalar. So basically, you take the like terms of the two matrices, multiply them, and add the product sum. So as you mentioned, identity matrix is a diagonal matrix. Okay, all the terms are zero except for the diagonal terms, which are all unity. Okay, so you take those terms, non-zero terms, because of course the terms coming from zero would be zero. You take those terms, that is the diagonal terms, and you take the also corresponding diagonal terms, multiply with do the multiplication for both matrices, and then keep adding the terms. So basically T11 times 1 plus T22 times 1 plus T33 times 1, right? Would you agree that is trace of T?
Yes, sir.
Right. So this inner product right here is trace of S, the deviatoric stress. And what is the trace of a deviatoric stress? Deviatoric traces trace কত? আচ্ছা, trace of S is trace of sigma minus sigma m times trace of identity matrix. Now, how much is the trace of identity matrix?
1, 3.
3.
3, right? So minus 3 sigma m. Trace of sigma minus 3 sigma m. What is sigma m?
Sigma x plus sigma y plus sigma z by 2, 3.
It is trace of sigma divided by 3. So it is trace of sigma minus trace of sigma. The trace of S is 0. The deviatoric trace is so designed that the trace should be 0. বোঝা গেল এটা?
Yes, sir.
কি বুঝছো বলো তো? আমি তো বুঝতে পারছি না, প্রথম দিন থেকে আজকে বোধহয় 15 দিন পড়ানো হলো, 15 দিন ধরে এই একই কথা বলে যাচ্ছি, একই কথা ইয়েস স্যার বলে বুঝছো, কিন্তু বুঝছো না। Anyways, but you see, you can look at it like you know like you are taking derivative of uv with respect to x. So you do like chain rule, del u del x v plus u del v del x. Okay, u times del v del x and v times del u del x, right? So a S inner product S not only can it be written as sigma inner product S, it can also be written as S inner product sigma. Okay, so that means substituting this expression of S not to the first S but to the second S. Okay, so basically এবার আমি যদি দেখি যে what I'm doing over here, it is not same as of course sigma inner product sigma. One of the stresses must be the deviatoric stress. Okay, it's not sigma inner product sigma, it is S inner product sigma or sigma inner product S. At least one of them should be the deviatoric stress. Okay, so my point is, when I do take the derivative of S inner product S with sigma, okay, so I actually get twice S. Okay, and that's where I'm jumping a few steps, but it can be shown. Okay, for example, if I take the first term and take derivative, what is del sigma? Del sigma, it is identity matrix. Okay, so essentially you have the deviatoric stress, and it's not identity matrix in second order, it's a fourth order identity matrix. Okay, so when multiplied with s, this simply gives you s, but you could have also represented it as s times sigma, and like u times del v del x right here. If you had taken the use the chain rule and taken the derivative of the second term, then also you have got s and this identity matrix on the right side, which would again give you s. So essentially, this derivative, it can be shown that gives you twice s. Okay, because this derivative is same as taking del del s, s inner product s. Why so? Because sigma m times I has no part to play in s inner product s. So when I think of sigma to be s plus sigma m times I, okay, then taking derivative of s with respect to sigma is same as taking derivative of s with respect to s. Okay, because the trace of this term, okay, sigma, has no part to play in the deviatoric part, and we have already shown that the deviatoric part and the hydrostatic part, they are orthogonal to one another, because you see this essentially would give you trace of s which is 0. Okay, so the deviatoric part and isotropic part are so designed that they are orthogonal to one another. Okay, and in principal coordinates, when you have three coordinates to represent stress and strain, there essentially they are three-dimensional vectors. Okay, the deviatoric stress and the stress, and they are actually true. Truly represented like two orthogonal 3D vectors. Okay, you see, because deviatoric stress do not depend upon the hydrostatic part of the stress. Okay, so taking derivative of s with respect to sigma is as good as taking derivative of s inner product s with respect to s. Okay, so okay, so it becomes twice s, or in other words, this can be written as one by twice sigma equivalent times 3 by 2 times 2 s. So 3 by 2 sigma equivalent times s. Okay, or in other words, the plastic strain increment is d lambda three by two d lambda sigma equivalent s. Okay, so this result is also important. This is Prandtl. I may be doing some mistake with the spellings. Prandtl-Ross equation, okay, which basically claims that the plastic strain increment is proportional to the deviatoric stress. Okay, and it can be shown that that is only true. That is only true when you are dealing with von Mises criteria, because you see with Tresca criteria, okay, so this is sigma 1. So this is the Tresca criteria right here. For this entire flat surface, there is a single normal to the surface. But the deviatoric stress, if this was the center of the deviatoric plane, the deviatoric stress keeps on changing. So in this case, it is not proportional to the deviatoric stress. Okay, but with von Mises criteria, you have this relation: the plastic strain increment is proportional to the deviatoric stress. Okay, so that can be obtained for von Mises criteria. So this is going to be the most important equation from this point onwards. Okay, so go through today's class. If you have confusion, ask me on Wednesday and get this thing cleared with. Okay, and you can go through your textbook. I can also suggest some other books actually. um, you can go through the book by Lubliner. Okay, so this is I hope you understood the derivation, but it is still going to be confusing. So I need you to go through very well with this part of it. বোঝা গেল কি বলছি?
ওকে স্যার।
হ্যাঁ স্যার।